Okay. Let's start with the definition. C is a, suppose C is a Riemann surface. Riemann surface with omega ui zi fi zi dzi K1C, a meromorphic one form on C, and gamma is a piecewise smooth curve on C, not containing the poles of omega, yani pollar tehlikeli değil mi? Kuyu gibi düşünün. Kuyuya düşmek iyi değil. And omega is union of omega i's is any partition of omega satisfying this omega I lies in ui. We define the integral denoted like this, integral of omega over the curve gamma as the sum of pieces zi dz. Okay. Yani ne yapıyorum? So on our Riemann surface, okay, I have some curve gamma, and on each open set, I have a piece of it. Let's say this is, let's say, ui, uj, uk. On this piece, I take, let's say, this part. So this is omega I part, and then I have omega j and omega k. So this one is the omega k part, omega j part, not omega, gamma j, and then gamma k. Okay. Partition means they are disjoint except the endpoints. Okay. These pieces are disjoint. So you just cut this into pieces. Each piece lies in some UI. And then what you do, you just integrate. So my differential form here is fi zi dzi, and on this piece I have gamma I, so I just integrate over that. Okay, and this is a piece of complex plane, and then on this place I integrate, and then just add them up. Of course, you should ask the following, why this is well defined, right? Some I could just, take partition differently and use maybe other coordinate systems. Would I get the same thing, right? So we should address that question. So the definition, kayıt yapıyorum değil mi bu arada? Evet. Okay. The definition is well defined. Definition is well defined. Okay. Because if gamma, let's say UI prime is another partition of gamma satisfying gamma I prime UI, then by the change of variable, formula for Zi, Ij, Zj, okay, şu olurdu. On this piece, UI, UI, Uj prime. Yani iki farklı şekilde partition yaptım. Bir partition'ın bir parçasıyla diğer partition'ın bir parçası kesişebilir. O kesişim noktasında Fi, Zi, Dzi integralini alıyorum. This is just J prime Fi. How do we change coordinates in the differential form? I write Rj, Zj, and then derivative of this gadget, d phi ij, zj. But you know this thing. So on the other coordinate system, I have this. But this is just equal to gamma I intersection gamma j prime fj zj dzj. Okay. Since Zi is equal to this gadget, here I am just putting, you know, this thing here, and dzi is just the derivative of this gadget. But then this thing is just by the definition of, you know, meromorphic forms, differential forms on Riemann surfaces. This thing, actually, these two are related like this. Therefore, this is equal to this gadget. And this gives me what? This gives me the following. Hence, so I have, hence, this summation okay, Fi, Zi, Dzi. This is just over I, and then J, I, J prime Fi Zi dzi. But this can be written as, I can interchange these two summations. Of course, here's, these partitions are, both of them are finite. Why is that? Well, we are integrating a curve, which is the image of a, interval. It's a compact gadget. Therefore, you can cover it with finitely many, coordinate systems. So these are all, finite sums. We are not taking, infinite length, curves, integrals over such curves. So this thing is I J F I. Bunu yazdım zaten, özür dilerim. Onu yazdım. Garip sesler geliyor ama benim kulağıma. Okay. Burası gene aynı. But here, instead of this, I write this gadget because, this thing is equal to this thing. We just showed that. And now you integrate over I. You sum over I. Şimdi bakın. So I have this piece of gamma J prime. It is covered by the open sets. So I have open sets like this. These are our UIs. And this thing is just, something like this. And then for some other I have this one, and then this one, and then let's say this one, and then this one. So if you sum over I, you just get integral over gamma J prime Fj Zj dzj. So what we see is then, this expression is the same as this expression. Therefore, it doesn't matter how you partition your curve, right? It doesn't matter how you partition your curve. The two summations give you the same answer. Therefore, defining integral of omega over gamma like this, makes sense. It is well defined because of this computation. Peki, şimdi kompleks geometrinin güzelliklerini göreceğiz. Stokes Theorem for holomorphic differentials. Suppose there is a Riemann surface with omega in C an open subset. So that its closure is compact. Ya bu her zaman doğru aslında. C değil mi? Şey olduğuna göre compact Riemann surface her zaman doğru olması lazım ama neyse. Boundary of this gamma a piecewise smooth curve. Piecewise smooth olduğu için, right, it's like this, you know. It may have some corners, but besides finitely many points, it's differentiable so that you can take integral over that, okay? If it is not piecewise differentiable, then you may not take integral. Integral may not exist. Smooth curve and omega a holomorphic differential holomorphic one form defined on an open set containing the closure of this gadget, then the integral of omega over omega is zero. Yani bütün bunları sıfırı elde etmek için yaptık. Okay, so our Riemann surface is this, let's say, a piece of that, and here I have some piecewise defined curve. Let's say this is, so this region is our omega, and the boundary, so this is the closure of omega, and this is the curve omega omega'nın boundary'si gamma, şöyle diyeyim, ve bunun closure'da bir başka open set'in içinde kalmış. Şöyle U ve bizim differential formumuz da, our differential form is defined on this open set. Okay. Now let's see why the integral is zero. Okay. Orada bıraktım. Okay. Proof. Subdivide this region into omega i's so that each omega I lies in some ui, and omega I intersection omega j is empty, and burada hani bu open set'i parçalara bölüyorum. Open subsetlerin kesişimi boş ama boundary'leri and each boundary omega I is a piecewise smooth curve. Smooth curve. Yani şöyle bir şey. R, let's say omega is this. This whole thing may not contain in an coordinate system. So what I do, we just divide this into pieces like this, okay? So that, so UI, sorry, not UI, I am sorry, omega I, so this whole thing is omega. Omega i's are these pieces. This omega is just the interior of this gadget, okay? Interior. So when you take the boundary of this, boundary of that is this gadget. Okay, so this is the boundary of omega I. Interiors are disjoint, but the boundaries are piecewise smooth curves like this. And each one is contained in an open set. So each one is contained in a coordinate system. Değil mi? Yani yaptığımız şey şu, bu region'ı parçalara bölüyorum. Öyle ki her bir parçayı artık ben C'nin içinde bir open set olarak görebiliyorum. Orada da integral almayı biliyorum. Yani işi kompleks düzleme indirip orada integral alıyoruz. Yaptığımız şey o. Şimdi bakalım. Şimdi using the local coordinate representations, we get, let's see what we get. Boundary omega I W. So on something like this, now on this piece, on the boundary of this one, our function, our form, so this is in UI, and on UI, I have the differential form. What was the differential form? Fi'di değil mi? Fi'di. Fi, Zi, dzi. Şimdi şey yapayım. İşlemi daha notasyonu basitleştirmek için sadece bu UI'ye kısıtladım. Notasyon daha da karışmasın diye burada hani bu ZI yerine direkt şöyle yazayım, tamam mı? FZ, DZ. Yani aslında I. Ama notasyon daha karışmasın diye şöyle yazayım. Şimdi şunu yapacağım. Bu f'in, this function f has real part and imaginary part. Real part is just, let's say, u xy plus imaginary part I xy. So this I is not this I. This is the complex I. This is the index I. Şey görüyorsunuz işte niye böyle yazdığımızı. dz de dx plus I times dy. So here, what we do is this. Our function f of z, f of x plus iy in complex coordinates. So this has real part uxy plus I times vxy, and z is just x plus iy. Therefore, dz is just dx plus I times dy. Okay, so from complex calculus, we have those. And then we have the product here. So the integral has real and imaginary parts. Değil mi? Kompleks fonksiyon integrali nasıl tarif ediliyor? İşte böyle. Fonksiyonu reel ve imajiner kısımlarını ayırıyorsunuz. Dz'i de ayırıyorsunuz. Ondan sonra onları çarpacaksınız. So we have omega over the boundary of omega I is equal to what? So I multiply these two. So the product has real and imaginary parts. Again, what is the real part? Real part is u dx minus v dy, right? Because I squared is minus 1. And then I have imaginary part, I times, what is that? V dx plus u dy. Okay, real and imaginary parts are like this. So let's do that. So I have the real part uxy dx minus vxy dy, and then imaginary part uxy dy plus vxy dx. Yani isterseniz şöyle yazayım yine. Şimdi ne yapacağız? Bu teorem neydi? Zaten Stokes teoremdi. Stokes teoremi kullanacağım. Now I am in, right, this is a piece of complex plane. So it's a piece of R2. I have functions of two variables, x and y. I have u times dx minus v times dy and so on. So we just use Stokes theorem here. Stokes. Ne diyor Stokes teoremi? Hatırlıyor musunuz? Ben hatırlamıyorum. Çünkü f dx plus g dy ise bir tane bölgenin boundary'sinde bu neye eşittir? Double integral, right? Over the whole region. Gx minus fy dx dy. Değil mi? Gy mı? Ama burada zaten şey var ya. Türevini alıyoruz çünkü evet, tamam. Doğrusu bu. Tamam. Şimdi buna uygularsak ne olacak? Bu omega I üzerinde integral. Şimdi G dediğim şey, so G is minus V, right? If I compare this one with this one, G is minus V. So X derivative of this, so minus V sub X minus F sub Y. F is this, so F sub Y, U sub Y, dx dy plus I times this gadget. So this time G is this. So X derivative of this, U sub X minus F sub Y. F sub Y. Bunun Y'ye göre V sub Y. Bu ifadeler nedir? U and F are the real and imaginary parts of a complex function, right? Our complex function F. Yani ona da F dedik tabii, her şey F oldu. Buradaki F ile o F aynı şey değil. We know that this is identically zero and this is identically zero. Why? By the Cauchy-Riemann equations, right? So by CR means Cauchy-Riemann equations. Onu biliyor muyuz? Herkes biliyor mu? Kompleks kalkülüs almayan var mı aranızda? Sen mi bilmiyorsun bir tek? Diğer herkes biliyor mu? Okey. Ne kadar zaman var? Tamam. Cauchy-Riemann equations. Şimdi yeah, of course. We need what? Oh, well, you don't have to write it. If you say, this is a two-dimensional gadget. So I always use one integral sign, but this is double integral. Integral over omega. This is single variable integral because it is the integral over a curve. But this is a double integral. But, if you want to feel better, I can put it like this. Tamam mı? Bir bakayım. Bunu yaptık. Stokes Theorem for Holomorphic Differentials. Okay. Bir tek şey söylemem lazım. Burada şimdi where was it? Okay, here. So we have seen that this integral is zero. What is that? It is integral over, this 1, 2, 3, 4, 5 pieces of curves. But my aim is to show that integral over this, whole boundary, outside boundary is zero. I showed that, integral over this is zero, but my aim is to show that integral over this big curve is zero. So how do I obtain that one? Well, we do the following. This is true for all, of course, gadgets, and we pick orientation. Let's say we pick orientation like this, positive orientation. So orientation, oriented like this integral is zero. Over this piece, it is again zero. And what is the orientation here? So this way, this way, this way, and this way. You see, this part of the curve is cancelled now because in one integral I have orientation this way, in the other one it is this way. Therefore, this thing is gone, right? This piece in one integral comes with plus sign, in the other one comes with negative sign. So they cancel each other. So I erase this one. And then I have this one. So it is integral over this. I go like this, go like this, go like this. And this is also zero. But you see, again, if I add all these integrals, in one of them, this will come with a plus sign. In the other one, this will come with a minus sign. So this is gone. This way, all these things will be canceled. So what is left? Just the boundary of the whole, region. Therefore, this will give us the following, that so when you add all these, nereye yazayım onu? Şuraya yazalım. Note that inner pieces of boundary omega i's will cancel out, and 0, which is what? It is just the sum over I of this gadget. Bu integrallerin her birisi 0. Integral, each of these integrals is 0 by Stokes theorem. So if you add them all, you get 0. But what we see is that, when you sum these integrals, the inner pieces cancel out, and what is left? Just the outer pieces of the boundary, and it is just omega. So it is just omega. Therefore, this integral is just 0. Tamam mı? Şimdi bir 2 dakika şeyden bahsedeyim. Neydi? Cauchy-Riemann equation'larından. Kompleks kalkülüste gördünüz. You have seen Cauchy-Riemann equations in complex calculus, but there is a nice geometric interpretation. How? You see, when you have, let's say, a function from R2 to R2, which will, regard as C also, then the differential of this, df, suppose this has fxy, has two coordinates, uxy, vxy. Okay, so what is the derivative of this? You take derivative with respect to x, derivative with respect to y. Doğru mu yapıyorum? Derivative with respect to x, derivative with respect to y. This thing at any point, if you evaluate at any point, it's a linear map actually. What it does, so this point is P, this is f of P. It's a linear map from this coordinate systems. And if you pick a vector here, V, this vector is mapped to where? dfp at V. So you just multiply this vector via this matrix. So it is mapped to something like this, okay? dfp-v. It's a R linear map. So dfp is an R linear map. What about if this function is complex, analytic, complex differentiable? You see, I have this function fxy, uxy, vxy. I can write it like this. Instead of xy, let me just write x plus iy. They are the same thing, just notation. This is u xy plus I xy. Now it's a function of complex variable, right? This is f of z. And this function is complex linear means, so if it is analytic, so this is f of z, is analytic at a point P, means its derivative is a C linear map. It exists and it is C linear. So it exists and it is C linear. C linear ne demek? So C linear means the following. Now look at this gadget. I have a vector here. I can multiply this vector by a complex number, not just real, but complex number. For example, I times V. I times V. And here I have the differential of this map, df. Okay. And this is, let's say, yok şöyle yapmıştım. df pv. And I can multiply this vector by I also. So this is I times df pv. And a linear map. This is actually a linear map from R2 to R2, but I may regard R2 as complex line. And then I ask that this map is complex linear. What does it mean? It means it should, you should be able to take, right? You should be able to do this. I times V. If this is complex linear, I can take this I outside. So analytic means exactly this. Its derivative map is complex linear. You can take I outside. But you know, what does this tells us about the components of F? You see, multiplying by I corresponds to what? To a vector. I times E1. So you have this vector E1. If you multiply by I, right, you just get this. Değil mi? Yani bu 1, 0, bu da 0, 1. Ona E vektörü diyoruz. Right? What about I times E2? E2. This is just actually I, right? E2 is just this vector. It is just actually I squared. So this is just I times I. So it is -1. And it means it is just -1, 0. So I times E1 is just E2. And I times E2 is just minus E1. So multiplying by I just rotates the plane 90 degrees counterclockwise, right? So in this basis, E2, E1, E2 multiplication by I, let's call it by J. So from R2 to R2, this is just, you take a vector and multiply it by I, okay? So this is complex multiplication. This J is given via which matrix? So it sends 1, 0 1, 0 is mapped to 0, 1. 0, 1 is mapped to minus 1, 0. So this is just 0, 1, minus 1, 0. Okay? And you can check that when you take square of this, if you take square, you just get 0, eksi 1. You just get minus 1, 0, 0, minus 1. So minus 1. Her şeyi eksi 1 ile çarpmak. Peki burada yaptığımız ne oldu o zaman? So what does this tells us? Burada neyi sildim ben? Ha, bu R lineerdi. Tamam, burayı silebilirim. Kompleks lineer olmak neydi? So complex linear means this. So this means what? You take this linear map and then you have this linear operation. So this is J times V, and this is just multiplying by I means multiplying by J, dfV. And this is true for all V. Therefore, dfJ should be J times df. So F is analytic at P if and only if its derivative is complex linear at the point P, and that is the same thing as just J times df is equal to df times J. Bu ne demek? Matris dilinde yazalım. Bu neydi? Eksi 1, 0, 0. Yok, yanlış yazdım. J neydi? J is just 0, 0, minus 1, 1, 0. What is df? Df is, onu yazmıştık. Neredeydi o? U sub x, U sub y, V sub x, V sub y. So this should be equal to V sub x, U sub x, U sub y, V sub x, V sub y. And here I have 0, minus 1, 1, 0. Open this up, you get what? 0, V sub x, 0, minus V sub y, U sub x, U sub y is equal to 0, U sub y, minus U sub x, V sub y, and minus V sub x. So what we see is then şurada. So a function is analytic if these two matrices are the same. This means what? U sub x should be V sub y, and U sub y should be minus V sub x. So these are the Cauchy-Riemann equations. Okay, so being analytic actually is something very geometric. Okay, geometric, meaning that its derivative map considered as a linear map from R2 to R2 commutes with this matrix. Okay, commutes with this matrix. Therefore, analytic functions are actually very geometric objects. Okay. Tam da zamanında bitirmişiz.